what we need in CCC, we need phase diagram. That's very easy to make. I'll tell 2 words. More difficult is to find the tie lines. That's a little bit more difficult. So how do we get a phase diagram? I'll just explain what we will do tomorrow in practice. For example, you have water, which an organic solvent. Do we ask if they have something we could do? I don't know if somebody has a phase diagram that cannot be found in literature and they would like to make it, because it's possible to make one in one afternoon. It's not very... You have one?
No.
If it's not published, you know, doing useful work, it's better than repeating known work. The good point of repeating known work, we are sure to succeed. Okay, so we have water, organic solvent, not soluble, and we are adding a compatible solvent with 2, and that's a type 1. If it's type 2 or type 0, it's the same, we can do it the same. So how do we do? For example, in that case, we will prepare a water blending solvent, say 25%. 25% of methanol, for example, and 75% water. So that will be this point, one phase. And then you make a titration, adding this solvent you are working on, drop by drop and shaking. So first drop, soluble, second drop, soluble, third drop, soluble, drop by drop, until you see here on the orange point, you need 2 phases appearing. And when you make the titration, it looks like it becomes cloudy. You touch it, it dissolves eventually. One more drop, it's cloudy, and then you get 2 phases. So you note this proportion. Then you prepare, for example, on this rapid drawing, 50-50 of blending solvent and water, this point. And same, you add 1 drop, 2 drops, drop, 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 drop. At one time it becomes cloudy, 1 more drop to be sure, and you get this composition. Then you make 75% blending solvent and 25% water, and same. Then on this one, you must prepare maybe a large tube, because you add volume, soluble, 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 soluble. So let's change another a big one. And at certain point, it becomes cloudy. So you get those 3 points. Then you can start on the other side, making blending solvent plus organic solvent. For example, I prepare 50-50, and adding water, going this way. And when you add water, at one point, it becomes cloudy. Then you have those 4 points. You find in literature this point, because that's solubility of water in the organic solvent, and solubility of organic solvent in water to get this point. And you have a good idea of the binodal curve. So it's not very difficult. I have, in the French courses, we have students of in between graduate and undergraduates that knows enough chemistry to do it, and you do that, and they do it. That's not difficult. Tie line now, that's more difficult. Personally, it's for tie line, when I want to be sure, I just prepare the composition I want to work with, and with Jan Gerhard parallel with the quaternary system, we parallelly did the same thing at the same time. You just analyze. Since I am in the Laboratoire des Sciences Analytiques, we have gas chromatography, we have everything like you have here. So you just analyze, and then you have no problem. If you know the composition, you will spot the location of the point. If you cannot analyze, there is trick that allow you to find where the tie line is. So this is estimation, tie line estimation. You prepare your composition X, noting carefully, I make this volume, this volume, this volume. If this is a volume diagram, or this mass, this mass, this mass, if this is a mass phase diagram. You not everything you put in. So you know where you are for sure. You are on this position X, and this position X split in two. The green one here and the red one on the top. So you look. For example, in that case, to make it simple, I say, oh, this split approximately in the middle. So my tie line cannot be this, because I am not in the middle. X must be in the middle of the tie line. So you look with your ruler, where can I find a way to have X in the middle? Because that's what I see. And that's approximately here. Of course, it could be a little bit more, a little bit less, but that gives you an interesting estimate where your tie line is. So X is probably this composition and probably that one, not that size, because X green would be too short and X red would be too long, and not that side because it's the opposite. X red would be too short and X green would be too long. So it's probably this one. That's a rough way to use the lever rule to find the tie line position. The best way is this one. I take this composition, use it, use a Carl Fisher determination of water content, and then I have the water content. And with gas chromatography, if it's ethyl acetate, for example, very easy to quantitate ethyl acetate by gas chromatography or heptane by gas chromatography. Okay, on those things. Now we make it even more difficult, going for solvent. How many solvents can we use maximum? No answer. As many as you want. The rule is you must have two phases. That's not difficult. You take random, you get your kits mixing, you probably get two phases, maybe three, so that's a problem. So we can go 4 solvents, we can go 5. I'll stop to 4. No worry, you see slide 11 from 12. So when we have 4 solvents, we can reduce to 3 parameters making percentage, but there is no way to go down to 2. We want to put any proportion of 4 solvents. So I put light on this HEMWAT system because it's very useful for natural products. So HEMWAT in English, it's, I saw you are calling it differently. It means hexane, ethyl acetate, methanol, water. Heptane, actually. I put heptane. It's not big difference. Heptane, ethyl acetate, methanol, water. Why heptane? Because heptane, for those that are in the medical side, heptane is odd number 7. Hexane is 6 even. And it's known that 6, 8, 10, 12, you have strong interference with the living organism. 7, 9, little interference, which means heptane is much less toxic than hexane. It's much more expensive, so I understand if you use hexane, but it doesn't make big difference. It's very, very similar. So heptane, water, methanol, and ethyl acetate. It must be shown in 4-dimensional. So what I did, I prepared a Walter Conway style slide, because there is no other way. This is it. So let's see, water, methanol, heptane, water, methanol, heptane. Damn, I will not be able to put it like I put it on the slide. Methanol, water, heptane, ethyl acetate. When you look this in 3D, you have different phases, and all are one ternary diagram. So for example, this is heptane, water, methanol, and you have a regular type 1 diagram with tie lines. You may not see, I'm sorry, you can look close when you leave. On that side you can see, that's better. This is water, ethyl acetate, methanol. That's a type 1 composition that we could do tomorrow. 2 phases, single phases. And this slide, that's the stupid side. Ethyl acetate, heptane, completely soluble, and methanol. Methanol, there is a little, it's not completely stupid. Here, you cannot see, but there is a little part which makes 2 phases. If not, it's single phases. And we have seen that one. And that one is heptane, ethyl acetate, water. Also, this one is very interesting. It works everywhere. You don't see any line on any binodal curves because it's 2 phases everywhere. Heptane and water are not soluble, or so small amount that I cannot show it on such big things. And ethyl acetate and water are not soluble also, and heptane and ethyl acetate are completely soluble. So here we have just tie lines, and the tie lines goes from pure water to the mixture of ethyl acetate and heptane you have selected. Okay, and now I combine those compounds, 4 compounds, and you can open it, and you have the HEMWAT liquid system. In this liquid system, we are defined a particular composition which is called Arizona. This is so let me see. This particular composition starts at, you can read, it starts at ethyl acetate water. So in the middle of water, and ethyl acetate is there. Okay. I should find. Okay, here. In the middle of water, ethyl acetate. And it goes to heptane, methanol. So heptane is there and methanol is there, and I will put this. That's why it's up. I cannot. Inside this line, that's the Arizona liquid system. Only this. So you see, it goes from heptane methanol 50-50 to water ethyl acetate, going through the whole diagram. So the rule is, like you have on the slide, A. Why it's called Arizona system? Because there is the guy that designed this. Its name is Margraf, Rodolphe Margraf. He split in 26. Why 26? Because there is exactly 26 letters. The first one was called A, the last one was called Z. You want one in between, no problem. As long as you respect this rule, it belongs to that line and it works. So you start with A. A is no heptane, 1 in ethyl acetate, no methanol, and 1 in water. So that's this point. Water, ethyl acetate, 6. And the last one, Z, it's the opposite. It's 1 heptane, 0 ethyl acetate, 1 methanol, 0 water. And in between, you always must keep those 2 equal to those 2 to stay on the line. If you don't keep those 2, and those, I mean ethyl acetate, heptane ethyl acetate, same number as water, methanol water, you are not on the line. You are, it works. I don't say it doesn't work. I say you are not on the line. Who cares about your line? Why are you so? It's very interesting to be on that line because we have continuous change on partition coefficient, only on that line. I mean, if you find partition coefficient on one point B, C, D on this series of proportion of solvent, then the log of this partition coefficient change with the amount of water you have in the system. So you can predict. That's very interesting. You can predict for all. If you have one, you can predict the other. So that's why it's interesting to move on that line. That's it. If you are interested in one compound only, you don't have to care about that line. You can use any composition of heptane, ethyl acetate, methanol, water, and choosing the best that's working best for you. But if you are interested to predict what will happen, you can say, okay, this C was okay, I'll try D. Or C was completely off, I'll try P or R on the other side. And of course, A, which is ethyl acetate water, is very polar. This is 100% water, ethyl acetate, that's a polar system. And the last one, Z, heptane and methanol, that's the one we used yesterday, it's very apolar. So it means on the line, going from one side to the other, you have a wide differing polarities range. That's why it's interesting to get different separation of your mixture. And that was slide 12 out of 12. Thank you for your attention.